you doing? Seb here from So Goods and Sounds. I welcome you to the fourth part of episode 1, VCAs and envelope following, where we'll take a look at the three-way VCA and the envelope extractor. These modules, they're not really related to each other in any way, but they're pretty small circuits, so I think I should be able to cover it all in about 20-ish minutes. It's also Christmas in a few days, so I thought I might dress appropriately for the occasion. Anyway, let's get stuck into it. So the first module that we'll take a look at is the three-way VCA down here. It isn't actually wired three ways at all. We don't put in one signal and get 3 copies like we do with the mod. But I took the noise toaster VCA circuit and copied it 3 times and just put that into the same module. And three-way rhymes nicer with VCA than 3 copy or something dumb like that. So what exactly is a VCA? The voltage controlled amplifier is what we can use to modulate the volume or the amplitude of a signal that we put into it. So we can create natural attacks and decays, or rises and falls, to the volume of an instrument or sound that we are trying to synthesize. So for example, if I hit this glass with a spoon, we get a very short and sharp noise. So the volume of the noise has a very fast attack and decay. But if I hit an imaginary Chinese gong right here, the volume of the cymbal has a very quick attack and then a very slow decay as the ringing of the cymbal slowly fades away. And imagine a car going past you on the street. The volume of the engine slowly rises up as it comes towards you, and then slowly decays away as it fades away into the distance. So this is what the VCA does. We can modulate the amplitude of a sound that we put into it, depending on the type of signal that we use to modulate that sound. We can use the envelope generator to create natural sounding attacks and decays, or we could use the LFO to create tremolo style effects, or we could use a high frequency oscillator to create AM synthesis, or we could even modulate modulation. So let's take a close up, and then we'll get stuck into some patches with it and hear what this thing actually sounds like. So we have an input, an output, a CV input, a depth control for the CV, and then an on-off switch to bypass the VCA entirely. This circuit is then copied 3 times to make the most of the available space on the module. Plus, you can never have too many VCAs. So let's get stuck into some patches with it. So normally when we're using a VCA, we don't put a signal through it directly, and instead use it as the last module in the chain. In this case, I have a tone from the oscillator going into the filter, and then into the VCA, and then into the mixer for recording. Normally a VCA won't allow a signal to pass through at all until a CV source has been applied. But if I move the cutoff of the filter, we still have a tiny little bit of bleed through of the signal. But I have the envelope generator connected through the cable into the buffered multiple. 1, so we have a visual representation of what the signal is doing, and 2, I didn't actually have a cable long enough to go from all the way over there to here. But if I now take the CV source and plug that into the VCA and move the cutoff, we can start to hear the pulse coming through as it affects the amplitude of the signal coming from the oscillator. But we can use the depth control to adjust how much of an effect the control voltage source has on the amplitude of the tone. From absolutely nothing to just the most minimal of amounts. We can also use the on-off switch to bypass the VCA entirely so that it has no effect whatsoever. But we can also take the same signal from the envelope generator and then place that into the filter. So now we can get almost bass sort of sounds. And if we play around with the attack and the decay of the envelope generator, We can hear how the envelope being created from the generator is affecting both the amplitude through the VCA and the cutoff through the filter. But if I now change this from the envelope generator to the LFO, we can start to get almost tremolo style effects. But the square wave itself is a bit clicky, so I've changed it to the integrated square wave where it's a bit softer. But the tremolo style effect is a bit more pronounced if we remove the CV source from the filter. So to demonstrate the tremolo effect through the synthesizer, we can also use a guitar and a guitar player.
Hey.
I've hired my friend Jackson here, who is a much better player than I am, to demonstrate how we can use this tremolo effect. So I know before that I said we don't normally take a signal directly into a VCA, but I just wanted to quickly demonstrate amplitude modulation with a high frequency signal. So we have one oscillator going into the VCA, and then another oscillator being used to modulate that signal. So if I unmute the mixer, we start to get these radio tuning sounds and resonant vocals again. And all manner of craziness in between. Alright, that's enough of that. So for this patch, I wanted to demonstrate how we can modulate modulation with the VCA. As you can see, there's a lot of patch cables going on. So let's quickly break down what we have going on here. If I unmute the signal, we just have a tone from the oscillator going through the filter. But down here at the bottom is where we are modulating our modulation. We first have our LFO going into the VCA. We then have the envelope generator creating a rising and falling control voltage. This is going into the bottom buffered multiple, which is being used as the control voltage for the VCA. We then take the signal out from the VCA and put it into the top buffered multiple, which is then connected to another patch cable, which will apply to a couple of different control voltage inputs. So if I move the cutoff again, and now stick this into the LFO in of the TTO, we can hear how the LFO is being modulated by the envelope generator. So it's rising and falling. That's my crappy demonstration of what's going on. So this has the effect of rising the pitch up and down. Now let's see what happens when we put this into the CV input on the filter. But let's take this back to the TTO. And I'll show you what happens when we swap the LFO and the envelope generator. So now, the envelope generator is being modulated by the LFO. So you can see that when the LFO turns off, it allows the envelope generator to create those laser sounds. Now let's connect this signal back into the filter and see what happens then. Alright, that's a bit annoying. So this is how we're able to modulate modulation through the VCA. So now that we've heard what the VCA sounds like, let's have a look at what's going on behind the panel and how the circuit actually works. This VCA design is actually one of the simplest ones out there, as it's quite literally just a transistor and a few biasing resistors. So let's take a look. So as we can see, I wasn't kidding when I said it was super simple. We have an N-channel JFET being used in its voltage controlled resistor mode with a few biasing resistors. The signal actually gets squashed a little bit, so we do get a slight loss in overall amplitude, but it still works well enough to create some cool sounds. We first take our input on the left hand side here, which is the drain pin of the JFET. We then take the output from the right hand side at the JFET source pin, which is also dropped across this 100k load resistor connected to 0 volts. We then take the CV input through this 500k potentiometer, which was originally just a 470k resistor, but I changed it to a pot so we can have a level or depth control, and this is then also connected to the gate pin of the JFET. We then have this 1M resistor here, also connected to 0 volts, which is used to bias the JFET's gate, allowing CV sources to affect the amplitude of the input signal most effectively. As voltage applied to the CV input is made more positive, the resistance between the drain and source pins of the JFET goes down, and therefore drops some of the signal through the 100k load resistor, and the rest onwards to other modules. And as the CV source voltage is made more negative, the resistance between the drain and source pins of the JFET goes up, therefore less of the signal is allowed to pass through to the output, and therefore drops the amplitude of the signal. Then at the top here, we have a single pole, single throw switch, where we can bypass the input signal away from the JFET and just directly onwards to the output. So as you can see, this whole module is a very simple circuit, which is why it was easy to just duplicate it 3 times onto the same circuit board. So now we have the 3-way VCA. So next, we move on to the envelope extractor. Normally this module is called an envelope follower, but I just think envelope extractor sounds way cooler, even if I did just have to abbreviate it to end of ext. A few months ago, I saw this video by Make Noise.
The envelope of a sound is another word for its amplitude over time. In a modular synth, envelope following is a procedure in which a sound's envelope is extracted and turned into a function in the form of control voltage. I'll use it with the DPO and Optimix to create a bass sound that is locked in rhythm with the drum loop. We do not have to hear the drum loop at all. Also, you do not have to use the extracted envelope to control amplitude.
And I thought, holy crap, that is one of the coolest things I've ever seen. I want to make a module that can do that. So I tested out a few schematics and ended up landing on another one by Ray from Music from Outer Space. And it worked perfectly, so I promptly made it into another module. Normally an envelope follower is a part of a larger module, but I'm all about breaking everything out into its individual modules. So now we have a small cute panel for the envelope extractor. So what exactly is envelope following or extraction? Envelope following is basically the act of detecting the amplitude of of a fast-moving AC signal. This could be music, a drum loop, a voice, anything basically, and then turning it into a slower moving DC signal that we can then use as a CV source for, say, the pitch on the TTO or the cutoff on the filter. So I've drawn an imaginary AC signal which has all kinds of peaks and troughs to it. And if we first remove the bottom half of the waveform, and that negative half of the waveform is then turned into a positive half. So now all parts of the AC signal only exist in the positive region. But it doesn't end there, because this signal is still moving much too fast to be used as a CV source. So we still need to be able to turn it into a DC signal. So to do this, if I draw a line that follows all the peaks of the waveform, so we now have a DC signal that follows the amplitude envelope of the AC signal. So this process is also known as full wave rectification, and this can now be used as a CV source for the filter or the TTO or the VCA. So taking a close-up, there really isn't much to see on the panel at all, but we basically have an input for the AC signal, an output for the DC signal to be used as a CV source, and then an LED to monitor what's happening on the output. My little drawing down here isn't exactly accurate for what the extractor does after our whiteboard explanation, but it still gives the idea and looks kind of funky. Well, that was it. Time for some patches with it. So for this patch, I thought we might try and recreate the Make Noise video that we saw just before, and we can also build up an idea of how the envelope extractor works. So I have a drum loop on the iPad going into the buffered multiple, where we can see the fast moving AC signal on the LED. This is then connected into the mixer, so that if I unmute the signal, we can hear the drum loop. But because this AC signal is moving much too fast to be used as a control voltage source, this is where we plug it into the envelope extractor. So I have another patch cable connected into the mult, so that we can then stick this into the envelope extractor. Now we can see how this LED is moving at a much slower rate compared to this one down here. So we have effectively created a slower moving DC signal out of an AC signal, and we can now use this as a control voltage source for any of the other modules, like the TTO or the filter or the VCA. So let's start building up a pretty big patch, and this is one of my favourite ones because it's the closest the machine comes to being actually musical. So let's get stuck into it. I'm going to first take an oscillator, take that into the filter, then now the filter into the VCA, then from the VCA over into the mixer. I'm also going to take the extracted envelope and put that into the top buffered multiple. So now that we have 3 copies of the signal that we can use around the system. So if I now unmute the mixer, we can hear our drum loop again. And our tone from the oscillator coming through the filter. But let's take one of the copies from the extracted envelope. And we'll first put that into the VCA where we can modulate the amplitude. Let's keep going. We'll take another one and put that into the filter. Let's keep going. We'll take another copy and we'll put that into the individual CV source. Interesting. How about if we take one of the copies and we'll put it into the quad attenuator, which basically creates an inversion of this signal. So now we can see that these LEDs are basically doing the opposite to one another. I might take that one into the filter. We can keep going with this patch for hours, so I think we'll leave it at that for now. So another one of my favourite patches to use with the envelope extractor is by putting in a music signal and then using that to shift the cutoff of a filter. So what we essentially get is an auto wah sort of effect, kind of like an old crybaby guitar pedal. So I have some music on the iPad again, copyright free as always, going into the buffered multiple, with one copy going into the filter and out into the mixer, and then another copy coming up into the envelope extractor, which we are then putting through one of the attenuators and then out into the control voltage input of the filter. So if I unmute the mixer and hit play on the music, we can hear how the cutoff of the filter is being shifted by the music itself. So we get this sort of auto wah sort of sound. Let's have a bit of a listen to a different song and see how that sounds. Now this auto-wah effect works much better with sort of slower sounding music compared to faster metal or punk, like this. There's just too much going on with this sort of music. Now another thing you can hear is that when the envelope extractor goes low, the filter is being pushed down, so we can't really hear the music anymore. This is why the envelope extracted signal is going into the attenuator, so we can then create the inverse of that signal. Now instead of the cutoff being pulled down, it's being pushed up. Now since it's Christmas time, I think we should have a listen to this song through the auto-wah. Bit of a trippy Christmas. As you can hear, this is one of my favourite patches to put music through, because it just makes everything sound really spacey and squelchy and out of this world. So as you heard, this module can be a lot of fun to create some pretty cool sounds. The circuit for this module was actually just one half of the wah pedal design, but I just got rid of the filter and kept the envelope follower, which is why it was easy to just turn it into a module more or less straight away, because all the biasing had been worked out for me already. So anyway, let's have a look at how the circuit works behind the panel. So first thing before we get into it, all the ground connections in this schematic are connected to actual ground at 0 volts. And all these VR1 points is where a connection is made to virtual ground at 6 volts. We first take our input from the left hand side here, where the signal is AC coupled through this cap here, and then fed into this inverting amplifier just here, which has a gain of about 6.3 volt per volt. The output signal of this inverting amplifier first goes into the anode of this diode down here, whose cathode is connected to both the non-inverting input of op-amp C here, and one end of the 1A resistor here going to actual ground. The output signal also goes through another AC coupling cap, and onto this unity gain inverting buffer made up of this op-amp just here. The output from the buffer is connected to another signal diode's anode just here, with the cathode connected to both the non-inverting input of the op-amp here and to the 1M resistor as well. Both of these two op-amps on the left work together to create a full wave rectifier, so we can create our DC signal from an AC signal. The positive half of the signal, coming out from the inverting amplifier, goes through D2 and is dropped onto the 1M resistor. The negative half of the signal is inverted by the inverting buffer and then goes through D1 and is also dropped onto the 1M resistor. If you were to measure the voltage peaks being dropped onto the 1M resistor, you would basically see the input signal's envelope. But next, we need to remove the input signal's content and just leave the envelope voltage. To do this, we use a low-pass filter on the voltage being fed into the non-inverting input of op-amp C, and then further filter the output from the op-amp with this resistor and capacitor just here. The envelope voltage is then buffered by the voltage follower, made up of this op-amp here, with the output being taken from the right-hand side. And now we have a voltage that follows the peaks of an AC signal's amplitude. On the output here, I also added the LED, just so we can have a visual display of what the output is doing. Well, I think that's it for today. This episode went on a bit longer than I anticipated, so I'm going to have to work on my time management skills, I think. I'll be back next year when we can finish off talking about how the rest of these modules work, and then start moving forward in my quest to create generative music. Have great holidays everyone, and I'll see you next time.